A blade tip gap can look insignificant, yet it connects two regions the blade is trying to keep apart. On an open-tipped axial or mixed-flow rotor, that small path can reshape the outer part of the passage. The useful question is not simply, how small is the gap? It is, what aerodynamic leakage and mechanical risk does this exact gap create? The blade produces pressure rise by maintaining a pressure difference between its pressure side and suction side. Near the casing, a clearance interrupts that separation. Air is driven through the gap by the local pressure difference, so the leakage depends on blade loading, tip geometry, casing shape, speed, operating point, density, and the reference boundary, not on clearance alone. The leakage does not remain a neat radial stream. It emerges as a jet, meets the main passage flow and rolls into a tip-leakage vortex. As the rotor turns, the vortex convects downstream and interacts with the next part of the blade passage. This animated vortex is a mechanism map, not a claim that every fan has the same vortex size or trajectory. Because some flow crosses the tip instead of following the intended blade loading, the outer span can become partly unloaded. The rotor may then deliver less useful turning or pressure contribution near the casing. Engineers sometimes describe this as a reduction in effective aerodynamic span, but the magnitude must be determined for the actual blade, gap, and duty point. The leakage jet and vortex also mix with the main flow. That mixing creates velocity gradients, entropy generation, and a region that can behave like aerodynamic blockage near the casing. The consequence may include lower pressure rise or efficiency, but there is no universal loss percentage. A small geometric change can matter differently at design flow, throttled flow, and high flow operation. Tip leakage can also change stability. Under some blade loading and inlet conditions, the leakage structure interacts with casing boundary layers and neighboring passages, influencing the onset or development of rotating disturbances. That can affect stall margin, but direction and magnitude are design-specific. Clearance should never be presented as a guaranteed stall cure. Noise is conditional too. Unsteady leakage, vortex interaction, blade-to-casing proximity and turbulence can alter broadband noise or discrete tones. Reducing a gap may reduce one excitation while exposing another mechanical or acoustic interaction. A defensible comparison needs matched speed, duty point, installation, microphone method, background correction and frequency data, not one headline decibel value. If leakage is undesirable, why not design zero clearance? Because the rotor and casing do not stay perfectly fixed. Manufacturing tolerances, assembly eccentricity, shaft runout, bearing motion, thermal growth, rotor deflection, casing distortion, and transient loads all consume clearance. A rub can damage a blade, casing, or bearing system, so aerodynamic ambition must remain inside a verified mechanical envelope. Think of the cold, stationary gap as only one line in a clearance budget. Stack the worst credible geometry and motion contributors, then check hot and rotating conditions, expected wear, mounting deformation, and measurement uncertainty. The governing minimum should be based on validated tolerances and operating states, not a photograph or a copied percentage from another fan. Real Longwell axial fan footage shows the practical rotor, guard, casing, and support arrangement, while the isolated impeller image makes the open blade tips easy to see. These visuals establish layout context only. They do not reveal a working clearance or prove a leakage loss. For inspection, the guard may need safe removal and the gap must be measured with a defined method at multiple circumferential and blade positions. A useful engineering review records fan family, blade and casing geometry, nominal and measured gap, measurement temperature, rotor position, runout, bearing condition, speed, operating point and acceptance basis. Then connect those observations to traceable performance or acoustic testing. If a change is proposed, validate both aerodynamic response and rub margin across the intended operating envelope. The decision rule is balanced: control tip leakage without sacrificing mechanical reliability. Compare like-for-like geometry and duty, measure the built machine, account for hot and rotating motion, and verify the result rather than assuming smaller is always better. Save this clearance review checklist for the next axial fan design or supplier discussion.